Bismillahirrahmanirrahim. There are at least two more questions regarding brittle failure, and I thought it would be good if I answered them here. The first one is K1C, or the fracture toughness. Is it a material property? Fracture toughness, it is also called the critical stress intensity factor. So is it a material property? Well, the answer is yes and no. Um, it turns out that thin plates are tougher than thick plates, and we don't need to go into details here. And if you test a thin plate and you subject it to the same stress levels as you subject a thicker plate, the answers are different. The fracture toughness of thinner plates are higher. So if you keep on testing plates of increasing thickness, then you'll get this kind of a curve. And then at a certain thickness, this is we are talking about thickness, and these are K1Cs. You measure them. After a certain thickness, it becomes constant. At that thickness and bigger for bigger thicknesses, K1C is a material property, and this is the so-called plane strain critical stress intensity factor. And the literature reports these values. You cannot report all these values for different thicknesses. So if your situation is the same situation, thickness is the same as the value as for the value reported, then you can use the value directly. But even if it is less than that, your thickness, you are operating here but you have reports in this region, then one thing is obvious. Even if you use that value, you are basically erring on the safe side. You'll not be surprised in an unpleasant way, but obviously it will result in an over design. So if you want to design in this region, either you use the same values, K1C for plane strain values for thin plates that you are using, and there will be a bigger factor of safety in that respect, or you can go for testing for your own thickness. So both these options are open for you. The second question pertains to is there a way to reinforce material so as to how to stop the cracks from propagating? Can we reinforce the material? Yes, we can. You may have heard about patches. This is the crack extending in this direction. You apply a patch here, and you stop the crack from lengthening for a while. This is to delay the propagation of crack. So this is one method, and for bodies in which the critical crack length is a long one, you can employ this method because you will notice the crack and you'll have time to put some reinforcement there. So for long critical crack lengths, obviously that will depend on the material. It will be a tough material most probably, and stress levels will be not that high. But when it comes to cracks that are not that long, critical crack length that not that long, you won't have time for this sort of thing. So in that case, you have to devise some mechanism which is already there in the body. For example, if I take another example of a comparatively low stress, it's the famous Liberty Bell. The crack propagated, and every once in a while somebody, now this is a patch, but you can blunt. This is the first, this blunting of the crack tip by drilling a hole. Now this is not exactly reinforcement of the material, but what you do is, this is the crack and it has every likelihood to grow. You drill a hole here, so you remove the stress concentration. So it will stop the crack from propagating for a while. Later on, after some time, it will still start, and then you have to drill another hole, and so on. So there's a limit to this kind of a process, and the Liberty well has a number of holes, and it's a very interesting study. Now, this sort of thing was also noticed in the failure of ships, that if the ships were riveted, then the crack was flowing and there was a rivet hole here, and the rivet hole also acts as the same thing. It was already there, but it blunted the crack, and oftentimes it stopped the crack. Even if it starts and then maybe changes its direction, and then there is another rivet hole and then it stops, so it delays the crack. And now riveted ships also had an advantage over welded ships. If the crack is here, and even if it reaches the end of this plate, the bottom plate, that's all. It won't enter this upper plate, because it's a different thing. It's not a homogeneous thing. It is not joined together in that way. If it's a welded shape, then they're just one piece, so it just runs through. So these things, it was fortunate that those ships that were saved, many a ship was saved because of rivet holes. But then when they shifted to welding, there were a lot of surprises. Now obviously we know how to design properly, so that you don't have to rely on the rivets to stop your cracks. But this is the uh, this is a concept that you must know, because there are only two methods of making a system tough. One is obviously if the system has a high work of fracture, and the metals have it, they have dislocations. For non-metals, obviously you don't have those mechanisms, but you have other mechanisms. So either you have to use those mechanisms, or you can uh, make it difficult for the crack to propagate. You make it difficult for it to propagate. One of the methods is this blunting of the crack tip. Now, for example, in non-metals, uh, biological materials, or even your uh, glass fiber materials, you have this sort of thing. You don't let the cracks to propagate, and how you achieve that is, for example, in this case, instead of reinforcing the material, we actually make it weaker. A homogeneous material just like this, you can look at the welding example. Two plates that are welded together, they are basically they are just one plate. You have to have different phases in a system for your crack to stop. So non-metals, biological materials, glass fibers, carbon fibers, they all utilize this sort of thing. What happens is, let's say this is a crack, and I'm talking about the famous Gordon-Cook mechanism. Obviously, we are talking about situations where you don't have time, you don't have so much time to put a patch there or keep on drilling, because these are, in any case, these are of less utility, practically speaking. Now you have to build this mechanism inside the material to start with, so that it takes care of itself. So what happens is, let's say this is a crack growing, this is a crack, now its length is growing. Now here's an interface. Now interface means there's a, let's say, matrix here, and there is a fiber here. Now this fiber is not, it doesn't stop the crack because it's very strong. In fact, fibers are very brittle materials. What happens is, when the crack reaches this point, there's a high stress here. So what happens is, this is an interface now. This is a different material. So homogeneity, just like the case with two steel plates welded together, that is not a beneficial thing. Here, you need to have different weakness planes. So if this plane is a plane of weakness, because two matrix and fiber are joined together here, they are not that strong, the interface is not that strong. So what happens is, there's a large stress here, and what happens is, when this crack reaches near this, this weakness opens up and it blunts the crack. And hence, not that it is very strong, but because the crack has lost its stress concentration, so it stops, and then it gets diverted and goes into some other direction, and then in that direction there is also a random fiber there, and so on. So it only delays the breakage, but it does valuable work in that way. So yes, the answer is you can reinforce, but reinforcing can be uh, so-called the reinforcing that we usually think of when we talk about reinforcing a material, but oftentimes it's about making the material with some interfaces that are weaker as compared to the rest. So it will uh, open up the crack face and then blunts it so that it doesn't move any further. Thank you very much.